Okay, let's talk about getting around, not, in your car, but
Yeah.
navigating these really interesting data structures, graphs.
Right. We've probably all bumped into trees before, those sort of neat hierarchies.
Predictable.
Yeah.
But graphs, they're different. They model connections, well, everywhere. Social networks, maps, software dependencies, the whole internet, really.
It's that flexibility that makes them so powerful, isn't it? Unlike trees, any node can pretty much connect to any other. That's why they're so good for real-world stuff.
Exactly. And when you've got this kind of complex web, the first thing is, how do you even explore it? How do you make sure you see everything, every node, every connection?
That's graph traversal, just
Yeah.
systematically visiting every vertex in the graph.
Right. And you mentioned trees.
Yeah, and it's worth remembering that tree traversal methods, pre-order, post-order, they're actually just special cases of graph traversal, just applied to that specific tree structure. Graphs are the bigger picture.
Uh-huh. Okay. So tree traversal is like a neat garden path, but graph traversal, that's like navigating a huge, maybe tangled jungle.
That's a good way to put it. And to explore that jungle, you need a strategy, an algorithm.
And our source for this deep dive, 9.3 graph traversal Hello Algo, lays out the two big ones, breadth first search, BFS, and depth first search, DFS.
Mm-hmm. And our mission today really is to unpack these. We want you to get how they work, like the actual mechanics, see the differences, and crucially, understand why they're so important for dealing with connected data. Hopefully make it stick.
Okay, let's kick off with BFS then, breadth first search. What's the main idea there? How does it explore?
BFS is all about going outwards, layer by layer. It's a near to far.
Near far, like ripples in a pond.
Exactly like that. Starting from one node, it visits all its immediate neighbors first distance 1. Then it visits all their unvisited neighbors distance 2, and so on. It systematically covers everything at one distance before moving further out.
The source has that visual, figure 9 to 9, showing that outward push. Closest nodes first, then the next layer, then the next. Feels very methodical.
It is. And to make that layer by layer thing happen smoothly, there's one data structure that's key. BFS relies heavily on a queue.
The queue. First in, first out. That makes total sense, doesn't it?
It does.
As you find nodes in the current layer, you add them to the back. When you need the next node to visit, you pull from the front, which will be one of the earliest ones you found, ensuring you stick to that layer order.
Precisely. You process a node, find its neighbors, which are in the next layer out, and you enqueue them. But there's another really critical bit, especially for graphs that might loop back on themselves.
Oh, right, cycles. You could get stuck going back and forth.
You could, so you need a way to remember where you've already been. That's the visited set.
The visited set, usually a hash set, right?
Yeah.
For quick lookups.
Yeah. It's like your logbook. Once a node is in the visited set, you know you've either processed it or it's already waiting in the queue, so you don't add it again. Prevents those infinite loops and make sure you only process each reachable node once.
Okay, crucial. So walk me through the steps then. How does it actually run?
Okay. You start with your initial vertex, add it to the queue, and add it to the visited set.
Got it. Queue has one, visited set has one, ready to go.
Right. Then you start a lip. The main condition is the queue empty? As long as it's not empty.
Keep go.
You dequeue a vertex from the front. This is the one you're currently visiting. You'd usually record it somewhere, like in a results list.
Okay, process that one. Now what?
Now you look at all its neighbors, all the vertices directly connected to it. For each of those neighbors,
Check the logbook.
check the visited set. Exactly. If that neighbor is not in the visited set,
It's a new discovery.
it's new. So you add it to the back of the queue to be processed later in its layer. And importantly, you immediately mark it as visited by adding it to the visited set right then.
Mark it visited when you enqueue it, not when you dequeue it later. That prevents adding duplicates to the queue if you find it via multiple paths, right?
Precisely. And that loop just keeps going. Dequeue, process, check neighbors, on-queue unvisited ones, and mark them visited until the queue is finally empty.
And when it's empty, you've hit everything reachable from the start, layer by layer. Okay, so the list of nodes you visited, is that order always the same if you start at the same node?
Interestingly, no. The source points out the BFS sequence is not unique.
Oh, really? I thought the layer-by-layer approach would make it fixed.
Well, the layers are fixed. You always visit all distance 1 nodes before any distance 2 nodes, and so on. But within a single layer, the order can change.
How so?
It depends on the order you happen to find and enqueue the neighbors from the previous layer. Say node A has neighbors B and C, both at the same distance. Your code might check B then C or C then B. That changes the order they go into the queue and thus the order they come out within that layer. Figure 910 in the source shows this well. Ah, okay. The layer structure is consistent, but the sequence inside a layer can vary based on implementation details.
Got it. Makes sense. Let's talk resources. How much time and space does BFS take?
Okay. For a graph with V vertices, that's the number of nodes and E edges, or connections. BFS time complexity is OV plus E.
V plus E. Why both?
Well, think it through. Every vertex, every node, gets put into the queue once and taken out once. That's proportional to V, so OV work.
Okay.
Then when you process each vertex, you have to look at all its outgoing edges to find its neighbors. Over the whole traversal, you end up looking at each edge. In an undirected graph, you look at it from both ends, essentially. So examining all the edges takes time proportional to E, OE.
You have it together.
And you get OV plus E. You basically touch every node and every edge.
Simple enough. And space. How much memory does it need?
Space complexity is OV.
OV. Where's that mainly used?
It comes from a few places. The visited set can store up to V nodes. The queue, in the worst case, might hold a large fraction of the nodes simultaneously, especially in dense graphs. And if you're storing the result sequence, that takes OV space too, so it scales with the number of vertices.
Okay, so BFS recap,
Yeah.
layer by layer, uses a queue, needs that visited set, OV plus E time, OV space. Feels good for finding, like, the closest things first, maybe shortest paths if the edges don't have weights.
Exactly. It's the go-to for shortest paths in unweighted graphs because it finds things in order of distance. Also great for network broadcasts, finding connected components, things like that.
Cool. All right, let's switch gears. The other big one, depth first search, DFS. If BFS goes wide, what's the DFS approach to that graph jungle?
DFS is philosophically different. Instead of spreading out, it dives deep. It commits to exploring one path as far as it can possibly go before it even considers alternatives.
Like going all the way down one corridor.
Yeah, exactly. Go deep, then backtrack. Start at a node, pick an unvisited neighbor, go to it, pick one of its unvisited neighbors, go to it. Keep pushing down that single branch until you hit a node that either has no neighbors or all its neighbors have already been visited.
A dead end, basically.
A dead end for that specific path, yeah. Then, and only then, does it pull back. It backtracks up the path to the last node where it had a choice of unexplored neighbors, and it picks a different one and dives down that new branch.
Ah, like exploring one tunnel fully, then returning to the last junction to try another tunnel. Intense focus on one path at a time.
Exactly. Figure 911 in the source gives a nice visual of this deep dive.
And how do you typically code this go deep then come back pattern? It sounds recursive.
It screams recursion. It's the most natural way to implement DFS.
Yeah.
You have a function that visits a node, then for each unvisited neighbor, it calls itself on that neighbor. And like BFS, you absolutely still need that visited set. Can't forget that.
Still need the visited set to avoid loops and revisiting. Okay, walk me through the recursive functions logic.
Okay, imagine a function, say DFS helper, that takes the current vertex, let's call it vet. First thing it does when it's called. Add vet to the result list, and crucially, add vet to the visited set. Mark your territorial.
Standard procedure. Visited and recorded.
Right. Then it looks at all adjacent vertices of vet. For each neighbor, let's call it adjuvet, it checks. Have we visited adjuvet before? Using the visited set.
Still checking the logbook.
Always. If adjuvant has not been visited, here's the magic.
Oh.
The DFS helper function calls itself recursively, passing in adjuvant.
Boom. Dive deeper. The current function call pauses, and a new one starts for the neighbor.
Exactly. And that new call marks adjuvant visited, processes it, looks at its neighbors, potentially making more recursive calls, going deeper and deeper down the chain.
Until
a call reaches a vertex where all its neighbors are already in the visited set. At that point, the loop checking neighbors finishes without making any more recursive calls.
So that specific function call just ends.
It finishes, and it returns. That return is the backtracking. Control pops back up the call stack to the function that called it, say, the call for the previous node, vet. And execution resumes right after the line where it made the recursive call for adjuvant.
And then that function call for vet continues its loop, checking if vet had any other unvisited neighbors it hasn't tried yet.
Spot on. If it finds another unvisited neighbor, it makes another recursive call, diving down a different branch. If it runs out of unvisited neighbors, its loop finishes and it returns, backtracking further up.
Wow, okay. It's this chain of diving down and popping back up. The source mentions figure 912 with those dashed lines.
Yeah, the downward recursion lines when you make a call and the upward backtracking curves when a call returns. Visualizing that stack, pushing and popping, really helps understand the flow.
It does. Okay, same question as BFS. Is the DFS traversal sequence unique?
Nope, also not unique. The source confirms this one too.
Okay, why not this time? Seems like go as deep as possible would force a specific path.
The choice point in DFS is when a vertex has multiple unvisited neighbors. Which one do you pick to dive into first? The algorithm doesn't specify. The order you happen to check the neighbors determines the entire subsequent path. Pick neighbor B first, you explore that whole branch. Pick neighbor C first, you explore that branch instead. Leads to different sequences.
Ah, right. So for BFS, the non-uniqueness is within a layer. For DFS, it's the choice of which branch to explore first at any junction. Different reasons, same outcome. The sequence can vary.
Exactly. And connecting back to trees again, the source mentions pre-order, in-order, post-order. These are all basically DFS. The difference is just when you visit the node relative to the recursive calls on its children. Pre-order visits before diving, post-order visits after returning from all dives.
Really drives home that trees are a special case.
Hmm.
Okay, complexity time for DFS, time and space.
This might be a bit surprising, but it's the same as BFS for general graphs. Time complexity is OV plus E.
Still OV plus E, even with all the recursion and backtracking overhead.
Yep. Because, again, assuming you use the visited set properly, each vertex gets visited and processed exactly once. That's OEV. And you still examine each edge when checking neighbors, typically twice in total for undirected graphs. That's OEE. The overall work is still tied to the number of vertices and edges.
Okay, fair enough. And space complexity, is it also OV?
It is OV. The space comes from the visited set, the result list, and critically for DFS, the recursion call stack.
Ah, the stack implicitly used by recursion.
Right. In the worst case, imagine a graph that's just a long line of nodes. The recursion could go V levels deep before it starts backtracking. That means the call stack needs space proportional to V. For bushier graphs, the depth might be less, but the worst case dictates OV.
So fascinating. Totally different ways of exploring wide versus deep, Q versus recursion stack, but they land on the same OV plus E time and OV space complexity. That's a key takeaway.
It really is. It tells you that just for the basic job of visiting everything, neither is inherently faster or slower in the worst case. The choice depends much more on what you're trying to do with the traversal.
Right. Like you said, BFS for shortest unweighted paths.
Mm-hmm.
What's DFS good for?
DFS is fantastic for things like checking connectivity. Can you get from A to B at all? Finding cycles in a graph, topological sorting, which is ordering tasks based on dependencies, super important in build systems or scheduling, and even solving mazes, where you need to explore one path deeply.
Okay, so let's nail down the comparison. Core differences, side by side.
Okay. DFS explores layer by layer, near to far, uses a queue, finds shortest paths in unweighted graphs naturally.
DFS explores deeply down one path before backtracking, go deep, then backtrack. Uses recursion, implicit stack. Good for connectivity, cycles, topological sort, pathfinding, and mazes.
And both absolutely rely on that visited set to handle cycles and avoid redundant work.
Different strategies, different tools, queue versus stack, same overall efficiency, OV plus E time, OV space. Yeah. Got it. So connecting this back to you, listening, why have we spent this time really digging into these two algorithms?
Because, honestly, they're fundamental. They are the building blocks. Anytime you're dealing with networks, relationships, any kind of interconnected data, you'll likely encounter BFS or DFS, or algorithms built upon them.
Like finding the quickest route on a map app.
Algorithms, like Dijkstra's, are related to BFS concepts, yeah? Checking if your network is segmented, DFS can help. Figuring out the build order for software, that's topological sort, using DFS crawling websites. Often starts with BFS or DFS principles.
So understanding them isn't just theory.
Not at all. It's about getting the core tools to systematically explore and make sense of these complex systems that are, frankly, everywhere. They let you navigate the unknown parts of the graph methodically.
Your essential graph navigation toolkit. Okay, so we've done a deep dive into breadth-first search and depth-first search. We looked at their strategies, BFS's layers via a queue, DFS's deep dives via recursion. We saw the crucial role of the visited set and confirmed their matching OV plus E time and OV space complexities.
And maybe something to chew on as we wrap up. We established that the exact traversal sequence isn't unique for either BFS or DFS. It depends on neighbor order. So if just finding all the nodes gives the same set of nodes eventually, what is it about the order or manner of traversal that makes one better for certain jobs than the other? It suggests that how they explore wide versus deep inherently reveals different things about the graph structure along the way, right? Something to think about next time you're trying to figure out how to approach a graph problem.
Absolutely. Good food for thought.
Yeah.
Keep exploring those connections, everyone.